all the other guys have the same information level like you have in the online session. Okay, so we have had the large signal characteristics and the small signal characteristics as a small deflection around an operating point, around the bias point. We have learned that the input characteristics of a bipolar transistor refers to the input voltage and input current. So it is a resistance. The slope is 1 over the resistance. And if we go to the output current, it is just multiplication times beta. Then we have the output current as a function of the input voltage. And this is the transmission characteristics. That's the most important chart of a transistor. So this transmission characteristics is for a MOSFET like this, nothing, and then it starts quadratically. Its increase. So its slope is far less than the slope for an exponential curve. To be clear here, and if we interpret this slope as a resistance, as an emitter resistance, oh, some compression artifacts. I just switch off the sharing and switch on the sharing again. The second part, switch on the sharing, takes more time than usual. Okay, no, it's good again from my point of view. Is it okay for you also? Yeah, it should work. Yeah. So, so the so-called the emitter resistance has a very low value. So depending on the port you are looking into electrically, you have different impedances. Be aware of these facts. Now we miss one more thing. It's the slope of the output characteristics. So the usual output characteristics I have plotted in this scale using this bipolar transistor, which is a standard small signal transistor. And if you plot that device and use a large scale, then you see the virtual elongation, the interpolation of the slope, that all of them does intersect at one point. So that's the model behind this transistor in LT-SPICE. So in the model, this transistor has a so-called early voltage. The early voltage itself has a positive sign. So the intersection is at negative voltages for sure, but the definition of the early voltage value is a positive value, just as a matter of fact. It's 63.2. The usual values are around 100. And we have learned that this slope is due to what? Due to this neutral base with modulation due to emitter collector voltage variation. This emitter collector voltage variation ends up to be base collector variation because emitter base voltage is roughly constant. Yep. Oh, many people. Hello, everybody. Now I have also seen you thanks to Mr. Botta. Hi. Um, Hello. Sorry for letting you waiting in the waiting room. And so this slope, the physical cause was the neutral base with modulation. The neutral base with modulation does make a slope variation of the diffusion charge triangle, and the slope variation makes the current variation. Okay, so after this slide, Mrs. Akbal, you can just drop your question you wanted to drop so all can participate to the answer. Just a comment of mine. Okay, so we have this current, the equation for this part of uh, the output characteristics. And for this part, we have this equation. And if we take this equation and take the first derivative for VCE, then we get again an exponential function divided by the early voltage. Why divided by the early voltage? Here we are, divided by the early voltage. That means this exponential function replicates itself divided by the early voltage. That means this slope is just a function of one parameter you can manipulate. It's the bias current. So the bias current, if you set it here, you have this slope. Sure. If you set your bias current here, then you have this slope. If you take a look to these curves from this perspective, it is for sure that it is only made by you by choosing the bias point, and physically by the transistor itself. So if you need a certain bias point, and if you need a certain slope, then you have to choose a different transistor or a different technology. Or you have to do circuit design. Because in the circuit design, as a cascode, we have learned that the cascode has a far more constant current as a function of the voltage at the output. So for the circuit design point of view, remember or take a closer look, if you can't remember because you have never heard about that, the cascode configuration. Mr. Rauscher, Mr. Fernando, and Mr. Friedl, they have learned that already. In the master's course, they are visiting the circuit design lectures. But the rest of you, it's not a topic of the examination. Don't worry, but take a look there. So let's calculate the differential output resistance of a transistor with the additional value I am giving you. What do you need in addition? You need in addition the bias current. And the bias current, we take the one I have given on previous slides. Typical values for analog design, 10 milliamperes here. Then we get 100 volts. That's the early voltage. That's not the value you are applying. It's a physical property of the bipolar transistor divided by 10 milliamps. That's a bias point. That's the bias. That's the operating point. Then we have as a unit ohm. 100 divided by 10 is 10. Divided by milli is kilo. So we have 10 kilo ohm. That means your slope corresponds to a 10 kilo ohm ohmic resistance. Why I'm saying so complicated, the 10 kilo ohm? Because now I'm giving you one aspect what is interesting from the circuit design point of view. Just take a blank sheet and say, okay, I'm using now voltage, current over voltage characteristics. I do this characteristics with an resistor, ohmic resistor. Then we have, if we have here 0 and we have a V1, then we have I1, and R is V1 divided by Y1. Boring, sure. Now, if you have a transistor which has the same differential resistance, then it has, one moment, let's put it just here, then it has usually some output characteristic curves. They look like these. Yeah, you know? Now just paint one, which looks like this. Okay? I'm just doing it. And so they are now parallel. Now you can see, or you should be able to see, that this current level here is reached by the transistor at much lower voltage levels, because you are looking at the slope, which is the same. So a differential resistor has not the same origin like an ohmic resistor. And this is the reason why you are using so-called active loads. What is an active load? A transistor, now I'm doing the sketch, how you do this measurement for this curve. You do this measurement for this curve by doing V bias. So we have here a certain VBE is equal to V bias, so it's constant. And then you measure different currents IC as a function of VCE. VCE. So you keep the voltage at the base constant, and you do a certain sweep of these two parameters. And the sweep of these two parameters gives you the so-called output characteristics. So, and these output characteristics give you then, for instance, this one, and then you see that you have much less voltage drop for the same effect of a large resistance. Okay, so I wanted to make this more clear by this sketch. But that's from the circuit design point of view, not from the semiconductor devices point of view. So that's not a topic for the examination. That's for your background. Well, let me give this summary, and then you are on the mic, Mrs. Akbar. The summary is, if we take a transistor and make small signal characteristics, we get the linearization of the input by the RBE. RBE we take from the slope in the bias point, and we get from the uh, nonlinear equations of the input, we get V temperature divided by EIB. So we see that the slope is just a function of the temperature and your operating point, not from the physical dimensions of the transistor itself. The transconductance is the most important function. Are your ears bloody now? It's the most important function. So if you can't give me this answer to the question, what is the most important curve in and for a transistor, then you can't pass the examination. That's the most important curve for a transistor. That's its transconductance. Yeah, it is the change of the collector current as a function of the base emitter voltage. And now you can interchange the vocabularies. For collector, you can say drain. Base emitter, you can say gate source. So, but basically, it is the same characteristics with different curvature. And for the bipolar transistor, we have an exponential one. Yep. And in the bias point, a small deviation in the input voltage causes a larger deviation of the output voltage along this slope, which is the transconductance. And this is a larger deviation in the current. This larger deviation in the current requires a much larger deviation at the collector emitter voltage to happen. This current change to be able to happen, you have to have this change. And if you compare now this voltage slope amplitude to this voltage amplitude, you see the maximum positive maximum voltage gain of a transistor. And this value is much larger compared to a MOSFET. Okay. Yeah, now I make a small stop to let Mrs. Akbal drop her question. Then we continue with our lectures. Okay, just drop me the question again. So we have the charge, we have the energy, and what we have again? The voltage. Okay, so the unit of the charge is Coulomb. It's ampere second. Okay, what is the unit of the energy? It is volt ampere second. And what is the unit of voltage? It's volt. Now you can see, well, if you take the energy divided by the charge and take these units, the energy divided by the charge, you get voltage. That's it. Okay? Question done? Okay. So it's fine with you? Great. So you can normalize the energy by the unit charge, then you get the equivalent value as a voltage. That's it. Okay. And therefore you can say electron volt. So you can say the band gap is 1 electron volt. That means in standard units, it is 1.6 times 10 to the power of minus 19. Okay. Ampere second as a charge times voltage. So one electron volt is equivalent to 1.610 to the power of minus 19 joule. So instead of having so bulky figures, you say electron volt. Okay. Yeah. Now, one more thing you have to know, but you can, after you have heard this, uh, just neglect it. Sorry about that. I have to just say it to you. You have from the output collector to the input base a certain feedback. Um, Here is nothing. So here we have no feedback. But in reality, you have a small resistive feedback. Why? Because we said initially the charge, the majorities here are injected to the base, and here they are minorities. There they pile up and say we have a diffusion delta n, and at this point the concentration is 0. Here we are at 0. Then we have a constant slope. Why? Because we said we have just diffusion, no recombination. But in reality, we have a small portion of recombination, really small. That means you have a certain change in the charge due to the recombination. And this changed charge makes your current, your slope, a function of the VBC in addition. That again makes you an additional small signal resistor to be taken into account, which is roughly, as a rule of thumb, RCE times 10 times beta. Now let's compare this value. This value is for our nominal bias, 10 kilo ohm. And this value is 10 kilo ohm times 10 times, what is our beta in our calculations? I have given this value once and then I have used it forever. So it sounds to be reasonable. So let's go back to 200, to the page here, times 200. Then we have 100, 1,000, 10,000, 20,000, and kilo 20 mega ohm. Is it true? Looks reasonable. If is it true? Yep, exactly. So 1, 2, 3, it's kilo. Kilo, it's mega. And 10 times 2 is 20. Yeah, it's true. So it's 20 mega. So if you have just 20 mega ohm in your feedback, it is roughly negligible. So the resistive feedback, you can say it's negligible. But the capacitive feedback, it's by far not negligible. So you know the collector base space charge for the Miller effect. So your Miller effect has to be taken into account as a dominant factor for feedback. Um, 1 second, please. I'm just calling for some water. One moment. I'm just switching off the microphone. Dennis, du hast mein Wasser wie vermutet vergessen. So, back again. The diffusion, the water is coming now by my son. um, Now we go over to take very important points in the frequency range into consideration. This gradient, this diffusion triangle, makes up our collector current. That's the most important point of the device. At the same time, it makes up a charge. Yeah, sure. You put in here particles, they put them here out, and we have a certain amount of charge. Let's calculate that value. If you calculate that value, you have a charge. And if you calculate the change, what is a changing charge as a function of the space charge region or as a function of the voltage? It's capacitance. So again, you take a charge and consider its change by changing the base emitter voltage. Then you end up having a small signal capacitance. This capacitance you can deposit in the equivalent circuit to the input. Now we have at the input a capacitor which is called diffusion capacitance at the input, at the Eingang, at the input, and you have your differential resistance at the input. Now let's calculate this capacitance. What is a charge? What is causing this charge? Let's go back. All the electrons which are injected and drift through the neutral base, they are there. How long? Tau c. It's the time, or it's tau b, tau c. I haven't remembered the index. I think it's tau b. It's tau. It's a time constant. Okay. And so it takes a certain time to pass this area. So if we have time times current, we have a charge. So let's define the charge by this equation. We are free to do that. Now let's go back to the slide where we are using this information. Okay, tau f, none of them were true. So it is the time to pass the neutral base for the electrons and the current level. It's the charge. So what is then constant? The transition time. So the change of the charge as of for IC is constant. If you increase the change of the charge, you increase the change of the current. Yeah. Okay. Now we take this equation and substitute this with here. So we put in one moment. No. I have just taken this part to here. So, I apologize. I have taken this part, so this part to here. I just separated them and added change in the collector current in the numerator and change in the collector current in the denominator. So what happens if you X them out? You have the same equation as before. So mathematically, you can do this. Just add this one. Now, we take a closer look at only this equation. And here you see that you get VBE is a function of IC in a certain bias point, and you get the slope. And the slope's name is GM. Here we are. And for this part, you compare it in, you see, the transition time. Okay, now we have a new definition of the diffusion capacitance. You can't avoid this diffusion capacitance. And the diffusion capacitance is shooting into your knees and says, "Here, happy day." I'm talking more about this happy day using bipolar transistors. It's not so happy. So the diffusion charge is proportional to the transconductance, the most important value in the transistor. Why? You have a base emitter voltage as a signal. You want to transfer this base emitter voltage to a collector current signal. And collector current signal you want to transfer into a voltage amplifier. So if you want to have more amplification, you want to have more transconductance. If you want to have more transconductance, you have a larger capacitance. If you have a larger capacitance, you have a larger time constant at the input. So if you plot here the so-called what is called the Bode diagram for the amplitude as a function of the frequency, then you have in the Bode diagram a low pass characteristics with minus 20 dB per decade in the frequency. And this corner frequency is 1 divided by 2 pi RC. And say what index? RBE, CDE. So, what happens? You apply here, you generate, no, you inject a current. Let's say you inject a current. Where does this current flow? It flows here and there. If your frequency is 0, the full current flows here. If your frequency is much, much larger than the corner frequency, then your full current is flowing here. So your active transistor doesn't see any voltage anymore. The whole signal current goes through the capacitance. So you have no active transistor anymore. So this is the corner frequency. Now let's calculate the time constant. RBE, we have learned it's VT divided by IB. The diffusion capacitance, we learned what? We learned that it is GM, GM is here, times tau f, tau f is here. So everything is known. Now let's calculate it. Let's take the values. You go to a small signal parameter measurement setup. What is that called? It's a so-called from S parameters. So the people who are interested more in measurement, you can take a look at S parameter measurements. From the S parameter measurements, you can recalculate the capacitance. So this is a measured value. And your transconductance, you can directly calculate here. We have learned that also. Give me, please, the transit frequencies, transit time for the electrons through the base. So I'm interested in what is the time of the electron to flow through the neutral base. We will calculate. Okay, one moment. One moment. The equation looks like now this. At the moment, if we want to have this, we have to put this into the denominator, and here we are. And then we add the values, picofarad, divided by, what is the transconductance? It is calculated by IC divided by VT. And this value you have already calculated with the nominal operating current, bias point, 10 milliamps. So 0.3 something you have given me. Can you go back in your... one moment. We have it in a not very far history. 391 Siemens, or 1 over ohm, is the transconductance. One second. So picosecond, and can you give me the figure again? That's it? Oh, 0.5. Okay. 1.58 is great. The rest we cut away. So the time of diffusion is this long through the base, through the neutral base. Okay. What is now the time constant of this transistor at the input? The time constant is, you say RBE, I don't know the operating point. Diffusion charge, you say I don't know the operating point. Then you put in the equations. It's VT divided by IB. That's RBE. You know, from this slope, VBE, IB. So this is the equation for that. For CDE, we have it already. It is here. And now we have a fantastic coincidence. VT is gone. IC is IB times beta. IB is gone. And left over is beta times tau, F. So your input corner frequency, your input time constant, can't be manipulated by you. It is given by technology, by beta, and by the time of flight. Let's calculate the value. $200, you're right. 50, ah, 30, 31, 31.7. So is it now okay? Nanosecond. Thank you very much. So 31.7 nanoseconds. That's a very large time constant. Now let's take a look at the transit frequency. What is the transit frequency? The transit frequency is, well, the transit frequency is where this current gain is 0 dB. That's the transit frequency. The definition of the transit frequency for a transistor, for a bipolar transistor, is the frequency at which the current you are putting in as a signal is equal, so the gain is 1. In dB, 1 is 0. So if the calculation of Q is 20 times 10 base logarithm of your gain, so your current gain. And if this value is equal to 1, your Q is 0 dB. So this is the definition of the transit frequency. And here we have just the equation. Can you give me now the frequency itself? Yeah. Okay. And can you give me this corner frequency? What does that mean for us? It means your bipolar transistor has a roughly constant current gain, up to 5 megahertz, and then its current gain is dropping due to your low pass characteristics. Then your current gain is 1, which is 0 dB, at 1 gigahertz. Now, if you take a look at the data sheet of a bipolar transistor, and if you see there 1 gigahertz, that doesn't mean you can use it at 1 gigahertz. It just means at 1 gigahertz, your current gain is 1. And if you want to use this transistor at 500 megahertz, well, you have not much left current gain. You have to be aware of that fact. And this fact, I have put it here again. Now, bandwidth in common emitter configuration. In common emitter configuration, the emitter is kept constant, your base is manipulated, and your collector is sensed. Okay, now the same game here. You put in a current signal. The signal produces only with this portion of your current a voltage which is multiplied by the beta 0, your nominal current gain. Then you have your current at the output. Now let's take a look IC, the output current signal current, to the input signal current, IC to IB dash. And this is due to this low pass filter characteristics, beta 0 divided by 1 plus J, or some mathematics can also say I, but in engineering I is used by current, so the engineers say J for the complex part of a complex current. So the imaginary part of a complex value is J times your time constant times omega. So that's the classical low pass filter characteristics, but for current, not for voltage. Okay, now we have learned that this one is given by physics, your current gain and your flight of time. And now your flight of time you can replace by the transit frequency. Your omega you can replace by 2 pi f for your operating frequency. So you get the operating frequency and your transit frequency into your resulting equation. And what do you see? You see that your frequency-dependent current gain is the nominal zero frequency current gain divided by a low-pass filter. And the corner frequency of this low-pass filter is given by this expression. What is the definition of corner frequency? If the real part of your expression is equal to the imaginary part of your expression. And it is here the case if 1 is equal to beta 0 f divided by ft. And this f is then fg by definition, the corner frequency. If this equality is valid, then your frequency is the corner frequency. So this you have learned in the second semester of your engineering, of your bachelor course. Now, in the Bode diagram, you just plot the absolute value either logarithmically in the value, or you can just calculate the so-called Pegel. It's 20 times log times this value here. So I have chosen to just plot the absolute values themselves. And here I have chosen, for the sake of simplicity, that my beta is 100, not 200. So don't be disturbed from this matter of fact. And your transit frequency is 1 gigahertz. Your corner frequency is 10 megahertz. And your slope is 20 dB per decade. It is a factor of 10, but a factor of 10 is using this equation 20 dB. So that means, to be clear, that I give you an example. One moment. My integrated circuits using silicon germanium to make 24 gigahertz amplifiers have had transistors which had 50 gigahertz transit frequency. Now my task was to operate these transistors here at 24 gigahertz. So what is left in the current game? So much. So it's like digging with a needle a hole. And if you dig with a needle, you have to be very exact in your simulations. And to be able to be exact in simulations, you have to make exact measurements to make models. And with these models, you can make simulations. Therefore, I'm telling you all this stuff with the transistor, its behavior in the physics, and the derived small signal parameters, and how you measure it, changing voltages, changing currents, so S parameters. And the result are these curves. So if you understand low pass filter, space charge, diffusion charge, you can basically make gigahertz circuits. But there are very many steps in between, for sure. For making measurements, you have to understand the measurement setup. Making models, you have to understand the models. But all of these topics can be reduced to these topics in this lecture. Diffusion charge, space charge, diffusion time, and low pass filter of first order. That's it. Okay, so the summary is we have a bipolar transistor with a differential resistance in the input. We have a diffusion charge mapped to the input, calculated by values given here. The time constant is indeed constant. Yeah. This you can neglect. Then the current which is flowing through this resistor times beta is this current. So you can transfer IB VBE. So you can say This current is not only Gm times VBE. You can say, so what is IB? IB is VBE divided by RBE. Okay, and your current here, I collector of X, let's say, and your I collector X is beta times IB, sorry. And this means it's beta times VBE divided by RBE. So you can express your current as a function of these values, beta, no, it's all. As a function of the voltage, as we have here a diode as a function of the resistance. You can also take this equation. And RCE, you have to remember on your imaginary eye, VCE as a function of IC, and it's this slope in an operating point, in a bias point. So if you take this small signal equivalent circuit, you should remember backwards how you calculate this. Let's put all the slides into this slide, which is relevant, okay? Start here. Start here. RBE, we have learned on slide 125. Okay. So 125, we have learned RBE. Now let's go back to RBE. Sorry. Where we have learned that it is an exponential function. We have learned it on this beautiful slide. Here, IB has an exponential function. On slide 114, where we have learned that this exponential function is exponential, we learned it here by the injection. Where we have learned that this injection is exponential, we have learned it we have learned it yeah, decades ago. Be patient with me, please. Don't fall asleep, because it's very important, because this is the way I want you to think about this topic. You have learned it here on slide 57. So I stop here. So everything is a chain, a red chain. So keep in mind these dependencies. And if you go back, you end up at the Fermi level, at the Fermi-Dirac statistics. So be aware if you learn for this oral examination, not the content, but the chain. Okay? That's the most important point for me that you have learned. The linkage of the information, not the information itself. Because we have Wikipedia for the information itself. and your own brain for the linkage of the information. Okay, so Wikipedia doesn't deliver all that stuff in in a nutshell. Okay, let's go back to the point where we are now, and we are now at the almost at the end of the bipolar transistor. Here we are. And all that stuff we could have done with the early voltage. No, with the differential resistance at the output. The reason for the differential resistance of the output is the early effect. The reason for the early effect is the change in the neutral base width. The change in the neutral base width is a function of the space charge change. The change in the space charge is a, yeah, blah, 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 blah. So take the same link chain for all these values. Then you have understand that stuff. Okay, what we have in addition? Yeah, we have in addition the junction capacitances. So the junction capacitance is nothing else but the space charge capacitance of a PN junction. So we have a junction capacitance at the emitter. It's the base emitter junction capacitance. We have between base and collector the space charge capacitance. Yeah, and we have in addition the series resistances. And what are the series resistances? Yeah, you know that already. I have painted them very often. That's RB. Now they have all some names. That's RC, and that's RE. And why I have put it here? Because we have some space charge boundaries. So I don't want to repeat all that stuff again and again, but here everything comes together. Okay, but we haven't talked much about these junction capacitances because we have said we are operating at low frequencies. And yeah, that's it. We're over. We have finished the lectures. That's all I wanted to tell you about devices. So, beginning from the atom to the crystal, from the crystal to the movable charge, from the movable charge to the control of the movable charge. They are moved by diffusion and drift, and you can control it by doping, by p doping, phosphorus, no, boron, by n doping, phosphorus, 5 valence electrons, boron 3 valence electrons. You put together these devices, you have p-n junctions. You put a third one, then you have n-p-n junction, then you have a bipolar. You have a circumstance, a certain condition that a bipolar operates as a transistor. You have to make the base small in the width to be able to transit all the injected charges. So we have a bipolar transistor. And if we take a metal oxide and a semiconductor, we have a stack of different materials. Then our reference was the vacuum level. We said that the work function is equal, that we have a flat band condition. And then we said, okay, what happens if we apply voltages? We said that we have bending of the band edge, and if these band edges cross the Fermi level, the intrinsic level, the Fermi level, then we invert the condition. It's an inversion layer. And if the inversion is twice the distance like the distance before you bend the band edge, then you have the strong inversion. And from these conditions, we calculated charges. From the charges, we calculated with using the capacitance, the voltage. And this voltage is the threshold voltage. So in these 3 minutes, you have learned the devices. These devices we have taken and made from the nonlinear equations a linearization in a bias point. And this linearization in a bias point is then used in the small signal equivalent circuit in circuit design. And this basics for the circuit design is laid down by taking a look at this small signal equivalent circuit. And if you have learned this, you can start making circuits. Full stop. Over. And finito. Um, by the way, do you have given me the evaluation? I need 6 evaluations. You have, Mr. Salak? Mrs. Akbal, do you have made the evaluation? You have received an email? Okay, right? That's great. Mrs. Akbal, I need also your evaluation. No. How is called the person? This is Wehinger Roth. One moment. I'm just copying the email you should have received. Important that you do all these evaluations. Hmm. So let's, Mrs. Akbal, please take a look into the chat window. I'm now trying to open the chat window. And there I'm copying the email address you should look at, look for. It's Bettina Wehinger-Roth. You see it in the chat? And she has sent you also, hopefully, I sent also your email address, an email with the Aufruf, with the call for evaluating my lecture. And if you don't do your evaluation, all the rest of the evaluations are worthless because I can't see then the results because you are too, not many people, you know? Oh, okay. Oh, try it. I think it works. Ah, Mr. Muka has already forwarded the link, Mrs. Akbal. Can you click on it and try to open whether you can do the evaluation itself? Yes, you can evaluate. You have to click on English and then it should work, hopefully. And then I'm very eager on your comments so that I can make some changes or drop something or add something. Hey, thank you. But critics are also very welcome because honest critics are very important. You don't get it often. If the number of reviewers are too less, I don't get any results, and I don't see the comments of all people. We have to be, I think, 6 or 5 or 6. Then I get the results anonymized. Okay. Well, then, as we are over now, I say we can skip the afternoon session if, yeah, one moment.